Welcome to 4.4 Graphing a Function Rule. Before we get started in this lesson, I would like to remind you that you need to have the 4.3 lesson check completed for tomorrow. So in this lesson, our goal is to graph equations that represent functions. So let's begin filling in our blanks. The set of all solutions of an equation forms the equation's graph. The set of all solutions of an equation forms the equation graph. A graph may include solutions that do not appear in the table. So that just means that on a graph there will be points that are not always in the table as well. And the last bullet point is a real-world graph should only show points that make sense in the given situation. So in a real-world situation, you just have to make sure that they would actually take place. So the points shown would actually take place in the situation. In example 1, we need to graph this function, y equals negative 2x plus 1. What we want to do first is make a table of values. So as you can see on your note sheet, we have the x values of negative 1, 0, 1, and 2. You want to write those down. And remember from previous lessons, the x values are the input values. So what we're going to do with those x values is input them, or plug them in, or substitute them in for the x. So in the middle column we will show our work, and on the right, in the right column we will plot, say our points, and then we'll eventually plot them. So in this first line, the negative 1 is going in for the x. We have negative 2 times negative 1, that's positive 2 plus 1 is 3. So our coordinate point is going to be negative 1, comma 3. We're going to do the same thing for the next 3 rows. I'll take you through 0, and then 1 and 2, I'll pause the video and write them down. You can catch up. So we're substituting in 0 for x. Negative 2 times 0 is 1, and you add 1 to 0 and you get 1. So the coordinate point here is 0, comma 1. We're going to do the exact same thing for 1 and 2, so try that on your own and compare with me in a second. For our input value of 1, we get an output value of negative 1, and for our input value of 2, we get an output value of negative 3. So our coordinate points are listed on the right column, and now we are going to graph those coordinate pairs and then connect them and have arrows at the end. So pause here and plot those points. Alright, our points are plotted, and we are connecting the points because we want our graph to represent all solutions. So the points in between the coordinate pairs that we plotted are also solutions to this equation. So that completes this first example. When we graph real-world functions, we need to have several things taken into consideration. First of all, we need to choose appropriate intervals for the units on our axes, which just means going up by 1, 2, 5, 15, 20, something like that, depending on the situation. And we need to make sure that our intervals are equal to each other. So have equal intervals on the axes, the x and y axis. Axes just means plural. And also, if all the data is non-negative, which means not negative, 0, or positive numbers, you only need to show the first quadrant. So once you have those blanks filled in, go over to the graph on the side of your note sheet and label the coordinates, or actually quadrants. Quadrant 1, quadrant 2, quadrant 3, and quadrant 4. It is always going to go in that order, so it's counterclockwise. Example 2 is a real-life situation. The function rule W equals 146C plus 30,000 represents the total weight W in pounds of a concrete mixer truck that carries C cubic feet of concrete. If the capacity of the truck is about 200 feet cubed, what is a reasonable graph of the function rule? As you can see, we have a table ready to go, and we also have a graph. So before we get to the graph, let's do the table. That will really help us figure out what coordinate pairs we should plot. So we have the table ready. We want to use C values of 0, 50, 100, 150, and 200. And the reason why I chose those values is because the least amount of concrete that the truck can hold is 0 cubic feet, obviously, if it was empty. And the most it can hold is 200 feet cubed because that is the capacity. And remember, capacity means the most that it can hold. So 0 to 200 is reasonable. So now what we're going to do is input the C value for the C in the equation. So we're going to have 146 times 0 plus 30,000. And obviously we get 30,000. That is the original weight of the truck. So with 0 cubic feet of concrete, we're going to have 30,000 pounds of weight for the truck. That's how much the truck actually weighs. And we're going to input the 50 now, and the 100, the 150, and the 200 next. So I'll take you through this step, and then after that we'll pause the video. You can do it on your own, and then we'll compare our values. When we multiply the 50 and the 146 and then add the 30,000, we get 37,000 pounds. So obviously we're definitely using a calculator's help for this problem. Okay, pause the video here and figure out what the W values that match up with the C values are. So there's the completed table. Feel free to pause again to catch up. And now what we're going to do is label our graph and plot the points and see what it looks like. We have our graph titled and labeled. The labels for the X and Y axes, the X axis is the concrete, and I wrote it off to the right corner because I can't write below, and then the Y label is the total weight of the truck. So as you can see, represented by the red segment is all of the concrete amounts and the total weight of the truck. Now you may be thinking, why am I not drawing an arrow after the 200? We have a segment and not a line here because there is a capacity of 200 feet cubed. So that's why we're stopping there. If there was not a capacity, then we could continue. But obviously trucks have a capacity of how much they can hold. That completes example 2. So feel free to pause there or flip over your packet for the remaining part of this lesson. Now let's talk about what continuous and discrete graphs are. A continuous graph is a graph that is unbroken or not broken. So a basic line is an example of a continuous function. And you will want to draw an example shown below and on your piece of paper. And the other kind of graph or function is called a discrete function, and this graphs as distinct points. They are isolated, so they're just dots that are in a line, but they are not connected. So there's holes in the graph, as you can see. Now in example 3, we're going to take a look at what continuous and discrete graphs look like in real life. Example 3, a local cheesemaker is making cheddar cheese to sell at a farmer's market. The amount of milk used to make the cheese and the price at which he sells the cheese are shown. Write a function for each situation. Graph each function, and is each graph continuous or discrete? So at left we have 1 gallon of milk makes 16 ounces of cheddar cheese. We're going to fill out the graphs, but before that we need to label the tables. Figure out what values go in there. So first of all, M stands for the number of gallons of milk and W stands for the weight of the cheese. We're going to define those variables right now. If we had 0 gallons of milk, we would obviously make 0 ounces of cheese. In the picture it said that if you have 1 gallon of milk, you have 16 ounces of cheese. If you have 2 gallons of milk, you would double that amount to get 32. If you had 3 gallons of milk, you would get 48, adding 16. And if you had 4 gallons of milk, you would get 64. So think about it for a second. What is the pattern? Well, we're adding 32 on the right column, so that means we're multiplying by 16. So we're adding 16 each time, and the faster way is to multiply by 16. And now we're going to plot those points and see what it looks like. We have our points plotted now. And let's think about it for a second. Does it make sense to connect the points? Like, is it possible to have 1.5 gallons of milk? Will we make a certain number of ounces of cheese? The answer to that question is yes. We should connect the points because it is possible to have, in between whole numbers of gallons. So let's connect the points now. We have our points connected, and it's not supposed to curve like that in the bottom corner. My computer's just malfunctioning. So anyways, is this continuous or not? Yes, it is continuous because any amount of milk makes sense. So we're going to connect the points and call it continuous. Any amount of milk makes sense. Now let's try the next part. Each wheel of cheddar cheese costs $9. So now N is going to be the number of cheese wheels and A is going to be the amount of money made from selling the cheese. So let's identify our variables now. The number of cheese wheels that we're going to try is 0, 1, 2, 3, and 4. So in the picture it says that each wheel of cheese costs $9. So if you get 0 wheels, it costs $0. If you get 1 wheel, it costs $9. If you get 2 wheels, it costs $18. If you get 3 wheels, it costs $27. And if you get 4 wheels, it costs $36. So do you see a pattern going on? We add 9 each time, so the faster way to do that is just to multiply by 9. So now take a moment to label your graph and plot the points, and we'll figure out if it's continuous or discrete. Now that our points are plotted on the graph, let's think about it for a second. Should we connect the points? Can this cheesemaker sell parts of wheels of cheese? The answer to that question is no. He can only sell whole wheels of cheese, so we will not connect the points, and that makes this graph discrete. So just to recap of that problem, the left side is a continuous function because it makes sense to use numbers in between whole gallons of milk, whereas the right graph is discrete because we cannot sell parts of wheels of cheese. It has to be a whole number. So that's it for example 3. We're getting really, really close to the end, so stick with me. We're so close. Okay, example 4. We need to learn how to graph nonlinear functions. And the easiest way to do this is to make a table and then graph the ordered pairs. So let's choose values for x of -4, -2, 0, 2, and 4. So write those down in the left column below the x. And what we're going to do, just as before, is we're going to plug in the x values, the inputs, and do our operations and get out the outputs. So I'll take you through the first one. -4 is going in. The absolute value symbols, those are absolute value. Remember what happens, it becomes positive or stays positive inside the symbols. So we have +4 -4, and that equals 0. So our first coordinate point is -4, 0. We're going to keep plugging in those values and figuring out what the output values match up with. So pause here and fill out the table, and we'll come back together in a second. Okay, our table is filled out. You can see the coordinate pairs on the right column, and now we're going to plot those points and see what this looks like. So there is our graph. This is called an absolute value function. As you can see, it's definitely not linear because it is not a straight line. So you can write absolute value function and move on to the last part of this example. Now let's try the function rule y equals x squared. We're going to input the x values of -2, -1, 0, 1, and 2. So let's input the -2. Remember to use parentheses. They are extremely important in this problem. So when you are squaring the -2, you have -2 times -2. That's a +4. So our coordinate point is -2, 4. We're going to input the -1 now. So -1 squared means -1 times itself, and that is +1. So -1 comma 1. We're inputting the 0. 0 squared is just 0. So we have 0, 0. Inputting the 1. 1 squared is 1. 1, 1. And the last one, inputting the 2. 2 squared is 4. 2 comma 4. So let's plot those points. We have -2, 4. -1, 1. 0, 0. 1, 1, and 2, 4. Connect those. Whoop, missed it. Let's try again. Okay, there is our graph. It is called a parabola. We will be looking at these more in depth later on in the school year. But as you can see, this is definitely not a linear function, so it's called nonlinear. That completes this section, so pat yourself on the back for completing this. This is the longest lesson so far. And make sure you do the lesson check from the previous section, 4.3, and you could try 4.4 lesson check now or wait until we do similar problems together during class. Great work!